All right, what I told you previously is your starting amount. Your starting amount. Yes, it goes over 1, but your starting amount is always the species whose concentration and amount you know. Whose concentration and volume you always know. Right, we know both the amount and concentration for KOH. We're going to start with the amount. We always start with the amount, not the concentration. Okay? You start with the amount of the species whose concentration you know. So we know 52.75 milliliters of this KOH solution. All right? I should have turned my paper sideways. But I made
HI as in high. There it is.
Yes, that's the acid, hydroiodic acid.
Right.
Okay. Shh. All right, since molarity is in liters, we know we're going to convert this to liters. So I'm going to do that. And you have to have an equality statement for that. The equality statement is that 1,000 milliliters equals 1 liter. If you don't have the equality statement, I will count off points on your test. You always have to have equality statements for conversion units. Okay? All right, so we've got that many milliliters of KOH solution. We're going to convert it to liters by doing 1,000 milliliters on the bottom and 1 liter on the top. And by doing that, then we can cancel milliliters, and we have our solution in liters. Okay? So now we're going to take that concentration. 0.200 molar is the same thing as 0.200 moles of KOH in 1 liter of KOH solution. So I can use that to convert to moles by putting the 0.200 moles of KOH. You have to know that's what these two things mean. Over 1 liter of KOH solution. If you don't know that that's what that means, you will not know how to do this. You have to know it. Okay? Well, now we can cancel liters by left off solution here. Okay, we can cancel liters. We can cancel KOH solution. I'm canceling as I go. I'm now at moles of KOH. But the question's asking me to find the concentration of the HI. So now I need a balanced equation. So I've got NaOH, which is a aqueous solution. I'm sorry, it's not NaOH, is it? It's KOH. Okay. And we've got HI. All right. And so what kind of equation do I have? What's the classification of the equation?
That would be a double replacement.
It's a double replacement reaction.
What's up?
So you would end up with water and
It would be Ki and then HOH.
Okay, good. Ki and HOH. In what physical state is HOH? What is that listed as? Liquid.
So there's dry pores.
Huh? I haven't done anything in either way right now. Okay? Okay. Now KOH, all I've done is a double replacement reaction here. Now, when we're classifying equations, this kind of equation had to be classified in two different ways. Double replacement and neutralization or acid base. Okay? You have to know that it's both. Okay? All right, now, that's just kind of an aside. Right now, we can just call it double replacement. Now I have a molar ratio. I'm trying to go from this to this. So I have 1 mole of this and 1 mole of that. All right? 1 mole KOH and 1 mole of HI. All right? I can cancel moles of KOH now. Now I'm going to have to go to another line. I should have turned my paper sideways maybe. Okay? Now, in order to get the concentration of the HI, that's what the question is asking for, I need to have it over liters. So I can have molar concentration. Molarity is always moles per liter of solution. So I need to get this into HI, moles, over liters of HI solution. I don't have liters of HI solution, but I do have milliliters of HI solution. So I can put 1 over 25.00 milliliters of HI solution and convert that to liters. Okay, using that same equality statement. 1,000 milliliters over 1 liter. Okay, so moles are going to be over liters when I'm done, canceling the milliliters. Okay? And we're ready to do the math. Okay, now here's a little bit of a shortcut. 1,000 on the bottom and 1,000 on the top are going to cancel.
Yeah.
Oh, that just saves a step.
Bam. What's up?
So can you cancel those? You
What?
just mark them out.
I just marked them out because they cancel. Okay? So 52.75 times 0.200.
I'm as confused as a blind dog in a meat house.
Okay? And let's see, then we got to divide, we had to hit enter and divide by 25.00. Okay, and so I get a molar concentration of 0.422, and that's moles of HI over liters of HI solution, so that is molarity HI solution.
Do you need the HI solution part, or just the molarity?
What now?
Do you need the HI solution part, or you can just
You have to say it's an HI solution, that's correct. Okay, now HI is a strong acid. I'm not sure if it's a gas or what it is when you start. Let's just say it's a gas when we start. Okay? And well, I'm not asking you to know. Okay?
when we do our equations, we're not going to count questions.
I'm not going to count up points if you're not required to know it. At this point, the only one of these acids that you're supposed to know, well, you should know that HCl is a gas. That's the only one so far that I think I've given you, where you know what physical state the pure substance is in. Okay? All right, so water's a liquid, and now we're going to use Bronsted-Lowry. Previously, we used Lewis, well, let's see, we didn't use Lewis, we used
Lewis dot.
Arrhenius. So if I dissociate, well, I didn't dissociate, yeah, this would be looking at acid in Arrhenius form.
How do you say
Bronsted-Lowry. Bronsted.
Arrhenius.
Well, this is Arrhenius here that I'm looking at on screen now,
Okay.
because I simply break up the acid to produce hydrogen ions in the water. That's the definition of an Arrhenius acid. Okay?
You're right.
Now, the Bronsted-Lowry acid says the hydrogens go to something else. Okay? So I'm using Bronsted-Lowry here, where we make hydronium, and the ion that's left over is I negative. Okay? Doesn't matter here, but it depends on what the question asks you.
Does it say H3O?
Yes, that's hydronium.
Right.
Okay?
Yep.
So it's a strong acid. Okay? So every one of these, every time I have a mole of these, I'm going to produce a mole of those. Does that make sense? For the same reason we talked about earlier. Right? Because it's a strong acid, it breaks up completely, right? Okay. So, if the hydroiodic acid concentration is 0.422 molar, because it's a strong acid, the hydronium ion concentration for that acid is also 0.422 molar. Okay? Because it's a strong acid and it's monoprotic, meaning it only has one hydrogen to dissociate. Whatever this concentration is, that's what this concentration is going to be. Has two what? Only has one hydrogen. What?
Like it has 3 hydrogens.
This is hydronium. That's we're not talking about that. We're talking about a hydrogen. The acid, the original acid, has one hydrogen to dissociate. Okay. This is technically an acid, but it only dissociates one of those. Because if you dissociate one, you have water, right? Okay, so either way, really, okay? But this is a monoprotic strong acid. This is not, well, this is technically, I suppose you could say it's a monoprotic strong acid because the second acid, second hydrogen, it's really hard to get it off, but it could happen. That's kind of beyond the scope of where we are.
Yeah, we don't.
All right, so that's the molar concentration of that original acid. Okay? All right, what is the OH? Well, a while ago we did a wheel that started with the hydrogen ion concentration. But that hydrogen ion concentration in the Arrhenius system is the hydronium ion concentration in the Bronsted-Lowry system. They are the same number. Look, in the Arrhenius system, you give away hydrogen ions. And for every one of these, you make one of those. In the Bronsted-Lowry system, you give away the hydrogen to water to make hydronium. Every one of these, you make one of those. So then, if the concentration of this is that, then it makes this concentration of hydronium in the Bronsted-Lowry system, and in the Arrhenius system, it's 0.422 molar as well.
So we're using
What?
So which one are we using to calculate?
They're the same number. Does it make any difference?
I mean, it is.
No, it doesn't. Because pH can be considered negative log of the hydrogen ion concentration if you're in the Arrhenius system, but that negative log of the hydrogen ion concentration in the Arrhenius system is the same thing as the negative log of the hydronium ion concentration in the Bronsted-Lowry system.
So which one do we break up into our H3O? The hydronium?
There's no OH here we're dealing with right now.
And what is the OH?
Yes, but you do that using our wheel.
Well, you just get all on top of it.
Yes.
So we can use either the Arrhenius or the Bronsted-Lowry?
Yeah. For this, it doesn't matter. Unless the question asks you to use one or the other, doesn't matter.
Okay, and we just have to know that if we use Arrhenius, we have to use the hydrogen, and if we use Bronsted-Lowry, we have
Yeah,
to use
hydronium. That's it. Okay. All right, so we know the answer to the concentration of the hydronium or the hydrogen. They're both 0.422 molar, right?
Times 10 to the 23rd.
No, molar.
I thought you said it was over that 6.02 times 10.
No, I'm saying a mole of these is 6.022 times 10 to the 23rd particles of it. Okay, that's all I'm saying, referring back to the Avogadro's number. Okay? All right. So we know that the hydronium ion concentration is equal to the hydrogen ion concentration, Bronsted-Lowry, Arrhenius, which is 0.422 molar.
Right.
So finding the hydroxide ion concentration comes from using that Kw equals the hydrogen ion times hydroxide ion concentration, which is also H3O plus and OH plus. Okay? This is Arrhenius. This is Bronsted-Lowry. Okay? So you can calculate this from that. Okay? Can you do it?
Hold up, let me get my count.
Well, what's KW? KW is always 1.0 times 10 to the negative 14 molar squared.
Oh, God, Josh.
Okay? So this divided by that, you get the answer, right? Isolate your unknown.
divided by what? What force is it? 2.36966846 times 10 to the negative 14. You have to write that whole thing out.
And then you round it off.
Good gracious.
Don't get mad at that, Breezy.
No.
What do you run it off with?
Kids both.
0.2.
Okay. We're going to use the multiplication division rules for rounding off these. Okay?
Round it off.
There actually is a different rule for exponents. We're not going to learn the exponent rounding rule. Okay? We're just going to use multiplication division rules. So, if our starting number had 3 digits, and we divided by a number that has only 2 digits, how many digits do we need in this answer? 2. We'll underline everything but the first 2 digits then. Okay? And so our concentration of OH is 2.4 times 10 to the negative 14 molar.
Why do we do that too? Because that's our only one.
Yeah.
Is
Okay?
that it?
Well, no. Let's find the pH now.
So we're done, right?
Wait,
No, pH.
Alright, we gotta find the pH.
It's got to be at least 2
So
decimals.
you rounded 1.0, 5,
Yep.
Okay. When you're doing all the constants over on the side, like under where it's actually doing, how do you do that?
What now?
All those constant things, what is that?
KW, we said by definition is the hydrogen ion molar concentration times the hydroxide ion molar concentration in the Arrhenius system. Therefore, KW is the hydronium ion molar concentration times the hydroxide ion concentration in the Bronsted-Lowry system. And the number for KW is always the same, 1.0 times 10 to the negative 14 molar squared.
So do we
All right.
make a log of that number?
Yeah. Well, of this number to find pH.
Wait. Okay.
Yeah.
How do you know to divide it by the 4.22? Sorry.
I can't hear you.
How do you know to divide it? Like,
You take, all right, well, if KW is this, and we know that, you find this by dividing both sides by that to isolate the unknown. Right?
Yeah.
Same stuff we learned, they've been doing in the last 2 units. You always isolate the unknown in a situation like that. Okay? All right, then. So pH is the negative logarithm of that number, right? I'm sorry, pH is the negative logarithm of that number.
how do you not use like a logarithm of the OH?
You could if you're trying to find the pOH. Right now we're trying to find the pH. The pH is the negative logarithm of the hydrogen ion or hydronium ion concentration. Okay? Negative log 0.422. So the pH is 0.374687.549, which we're going to round off to 2 digits.
Why do we want to do it in 3?
Oh, you're right. We can round it off to 3 there. Thank you. Okay. And that comes out to be 0.375 is the pH. Okay? All right? I want to find the pOH. Now I can find it in one of 2 ways. I can find the pOH in one of 2 ways. I could take the negative logarithm of that number, or I can subtract this number from 14. Okay? If you look at our wheel over here, we can find the pOH going from here to here, or from here to here.
Do it from here to here.
there
What?
to there.
Tell you what, this half of the class, on the left side, my left, your right,
Subtract.
you can subtract. And you guys are going to do the negative logarithm. Negative logarithm on that side, subtraction on this side. Negative logarithm.
Got it.
375 equals.
What number?
Oh yeah,
Oh,
baby.
wow, I forgot about that.
Oh yeah.
Find it. Okay, okay.
So using subtraction, I got 13.625.
That's what I got.
Okay. We're going to round it off to 3 digits. And I get 13.6, right? Okay. Using the negative logarithm.
Get 13.61.
All right, let's see. We're starting with this number right here.
Woo!
Negative logarithm.
Okay.
2.4
2.4.
e negative 14.
You're right.
I get 13.619, so forth and so forth and so forth.
Right, right.
Pretty darn close.
Yep.
Oh, when you round off, it'll be
Okay, which we round off. This one we have to round off to 2 digits. And so we get a pH of 14. But you're right. It looks like it's about the same number, isn't it? Okay?
It's in that vicinity.
Okay? And because we're not doing the rounding rules that actually apply to exponents and logarithms, that's why we get a little bit different number going both ways. Does that make sense?
Kinda, sorta.
Yes.
When we're doing this, do we have to like write out that we did the negative logarithm?
You always have to show me your work. Always show me your work. All right, guys, we got about half an hour left in the class. I'm going to let you spend that half an hour working on your practice test, okay? Ben, you had a question? I'm sorry, I can't hear you. Guys, you must be quiet. All right, Ben, go ahead.
How would you do the molarity for a diprotic or triprotic acid?
Okay, that's a very good question. If you have a diprotic or triprotic acid, the best you can do through using these kind of calculations is to know that if you calculate the molarity of a diprotic acid, for instance, you know because that second acid, that second proton is weak, it's going to be something less than that. You really can't calculate it directly. To actually calculate that, there is a way to do that, and in AP Chemistry you have to. You have to use something called the acid ionization constant to get there. Okay, but we don't do that in this level class. Okay, you won't have to worry about that. You have to estimate by saying it's less than this number or more than this number or something. Okay. Well, you have to know enough about the way it works to say it's less than this. So if I have a monoprotic weak acid, I could calculate the molarity directly. Okay, and say, okay, if I have, let's say I have 0.1 molar acetic acid, which is weak. All right, it's a monoprotic weak acid. That means that the molar concentration of the hydrogen ion. Please be quiet and listen. Just a second. Just a second. I'll get with you. Okay.
Ew.
If it's a monoprotic weak acid and I have 0.1 molar of that monoprotic weak acid, then I know the concentration of hydrogen ions has to be something less than that. That makes sense?
Right.
So, I mean, that's all you can say using just the calculation we have so far. But it's a good estimate, and when you get to doing acid ionization constants in AP, if you're doing that, then, you know, you've got a basis to make, at least say, oh, that looks reasonable or doesn't look reasonable, okay?